All right, a sphere is projected horizontally. The sphere is photographed at intervals of 0.10 seconds. The images of the sphere are shown against a grid on the diagram. Air resistance is negligible. Okay, so use data from the diagram to determine the acceleration of free fall, right? So what you got to understand is this is at 0 seconds, this is at 0.1, 0.2 seconds, 0.3, 0.4, 0.5, and 0.6. So I think to determine the acceleration of free fall, I'm going to use S is 1/2 AT squared, okay, which is, of course, the initial velocity is 0, right? And that's, of course, going to be the vertical S. So what you got to do is figure out where this guy is. See if I can do this. I still didn't do it very well. Right. Now keep in mind they've made this graph hard to read. This is 1.8, 1.6, 1.8. This is 1.7. So notice that between 1.7 and 1.8 there are actually 5 divisions and not 10, right? So figure out what that line is there. I think it's actually halfway between 1.7 and 1.8. So that's your S. Read the vertical, right? And then of course the time of that last one is 0.6 seconds. So you know the T, you know the S. You should use one of these last points, actually the last point, because of course here it hasn't gone very far. So our uncertainty of reading this, I might be off by half a square or something like that. That's a larger portion of the thing I'm reading. So it makes sense to use the farthest point, right? And then it says, determine the speed of the sphere 1.2 seconds after the release. And of course, it's going to have a horizontal velocity. It's going to have a vertical velocity of 1.2 seconds, right? And the speed is going to be the hypotenuse. This will be the speed, okay? So it's going to be literally, once we figure out the horizontal velocity at 1.2 seconds and the vertical velocity, it will be the square root of the horizontal squared, right? Plus the vertical squared. Okay, so how do we figure out the vertical velocity? That's easy, right? Just use V as U plus AT. Don't use the acceleration of gravity. Use the value that you get from this, okay? And it's going to be, I'll give you a clue, it's slightly, when you do this first one, it's slightly less than 9.81, but just go with it, okay? And then the initial vertical velocity, this is our vertical, right, is 0 because it's projected horizontally, right? So this is for our vertical. That's this guy, right? So just bust that out, right? And then the horizontal velocity, we're going to have to do a little graph reading here. The horizontal is just going to be S divided by T. Figure out what this S is. How far over does this go? Did I do that right? I'm a little bit to the left of it, right? So figure out what that is on the scale. Notice that now they're dividing 0.5 into 10 equal parts. So again, they're making the graph challenging to read, but we can do that. So figure out what that S is. Divide by, of course, in this dot here is 0.6 seconds, right? And that's going to be something, right? The horizontal velocity. I get a horizontal velocity between 3 and 4. I get the vertical velocity between 10 and 15. Okay, but it's negative, right? And there you go. And then the final thing it says, on the graph, draw the path of the sphere, assuming that air resistance is not negligible. Well, this means that it's going to not be as far to the right, and it's going to be progressively not as far to the right. So here it might be just a little bit to the left of this, right? As far as the right. Here it'll be a little more to the left of it, a little more to the left of it, a little more to the left, a little more, et cetera, right? Because it's going to decelerate horizontally. And then vertically, it's of course not going to be as far down. So here it's going to be just a little bit higher than that, a little bit even more higher, right? Your dots, you can just put a dot there and then connect those dots, right? Draw a nice smooth line through them. It is going to be on this side of that line. I'll give you that clue. See if you can do that.